Hello all, this is a brief little video talking about the transformations of graphs. Now if we understand what a typical graph is supposed to look like and we see it in a particular form, which is our generic little vertex type of form or something of that sort, we can apply these transformations and be able to graph our equation very quickly by understanding what the original graph would look like and then how to manipulate that. So for example, we have a typical quadratic equation here first, which is y equals x squared. The highest exponent is a square. There's nothing done to that, it's just simply a y equals x squared, and your graph would look something like this. It's called a parabola, and it goes through 0, 0, and we have some other points. We have some nice symmetry to it, and that's what a quadratic equation would graph like. We will talk about how these get changed. Another type of example of a graph would be a cubic function, something simply just y equals x cubed, which kind of looks similar to your parabola except 1/2 bent downwards, and it's a little bit skinnier because the cube allows us to increase or decrease our y values much more rapidly. We have a few others as well. The typical equation of a radical function looks like the orange one here on top. That's y is equal to the square root of x. Once again, it goes through 0, 0, and it kind of looks like your parabola, but it fell over to the side and the bottom half crashed into the ground and it is no longer there. It's complete ruins and rubble, but you can still see the top half of that parabola type of shape still standing there nicely. And another type of equation that we've talked about is the absolute value equation. And those are V-shaped, very pointed here at 0, 0. Once again, that would just be y is equal to the absolute value of x. So those are what some of our generic equations look like. So when we just look at the equation and we can see what the exponent is, or whether it has a radical or an absolute value, we know the general shape of that graph. However, the graphs have changes to them, some manipulations, and each equation that we have has a standard form that has the similar components. Okay. Here are our generic equations, if you wish to call them that. Quadratic equation would be y is equal to a times the quantity of x minus h, that quantity squared, and plus k. Cubic equations is very similar, but it's going to be a cubic function. That's how you know it's x to the third up there. A radical equation, that x minus h is going to be underneath the radical sign, and then of course similarly the absolute value has the x minus h and absolute value signs instead. But notice all the similarities. Each one has an a minus h, and a plus k. Each of those is going to affect the graph, right, in a different way. And we're just going to briefly talk about how that's going to affect our graphs. So to do that, we're going to examine the cubic equation. Once again, here's the typical equation or graph of y equals x cubed. Nothing fancy going on there. I just did this by hand. I did not go for exact answers, so don't be looking for little hash marks to find out points. I just know that the generic shape of a cubic function is this little snaky guy. So that's just a simple y is equal to x third. Now remember, we have these shifts that could occur. Now what would happen if, say, I wanted to find out what the graph of y equals x cubed plus 2 looks like? Now, I'm relating this new equation to what the generic equation looks like. There's no quantity inside here with the cube, so that's not an h value. There's no number in front of the x, so there's no a value. So what's being added here at the end is our k value. So if I was graphing this, how does that k, how does that plus 2 change or affect our graph? And what happens here is, you notice that the point here where it changes directions is at 0, 0. If I put 0, 0 in here, it would no longer work. Putting 0 in for the x and cubing it is still 0, but then my y value becomes 0 plus 2, which is a 2. So instead of this point going through 0, 0, it goes through the point 0, 2. So the entire graph ends up shifting upwards 2 units. So that plus k at the end has a vertical shift to it. or it shifts along the y-axis. If I was graphing instead something like y is equal to x cubed minus 3, this would shift our graph 3 units in the negative, because the sign in front of the term goes with the term, in the negative direction. So instead of having this graph, which is what we know is y equals x cubed, the entire thing would just shift 3 units downwards, and we'd have this graph instead. So the k does a vertical shift. Now, what happens with that h value inside that's close to the x? What happens if I have y is equal to the quantity of x minus 2 cubed? How is that going to change or affect my graph? Well, how it changes when it's close to the x is going to be along the x-axis. Now here's where you have to be very careful though. Since the quantity inside here says x minus, minus is part of the formula and not the value of that number. How am I shifting it? The h value is actually a positive 2. So even though it looks like I'm subtracting 2, the shift is going to be a horizontal shift because it's on the x-axis, it's close to the x value, and it's the opposite way of what it looks like. It looks like a negative 2, so it looks like we should be shifting left, but instead we shift right. So this graph would just change and move to the right 2 units. Once again, it's the opposite of what we think because the general formula says x minus that h value. So that would shift it to the right. So then what would shift it to the left? Y is equal to x plus 1 quantity cubed. The 1 plus 1 is inside. Now remember, the generic form is x minus, so really this is saying x minus a negative 1. So what is being shifted? It's being shifted a negative 1 units, which is why it shifts to the left 1 unit. So the h value inside is a horizontal shift. And I always say it goes the opposite of what we think it should. The k, or the vertical shift, goes the direction we expect. This was up, this was down. The horizontal shift does the opposite of what we think it should. So the k is that vertical shift, and the h is the horizontal shift. So what does a do? Well, a does a couple different things for us. First of all, we need to identify if a is positive or negative. If a is positive, then our graph looks as it does here. It has that positive type of slope, and it rises from left to right. Your snake is going up. So if a is greater than 0, we are rising left to right. The graph rises left to right. If a is negative or less than 0, the graph flips. So instead of it going up like this, it's going to flip over and it'll be falling from left to right. So the graph flips if it's negative, if a is negative, and it falls left to right. Now that's not the only change or effect that a can have on the graph. A also either stretches or shrinks your graph. Okay? So if a is a number that's greater than 1, okay? And technically it's the absolute value being greater than 1. So if the whole graph was flipped and the a value was a negative 2, this would be the same situation. So to be politically correct in math land, we should have the absolute value bars around it. But essentially, if your A value ignoring, if we just think of the A, the positive, negative, rising or falling, then look at that number without the sign. And if that number is greater than 1, then your graph is going to get skinnier, because that means that whatever we have down here that we're cubing, we then multiply that number by maybe a 2 or a 3 or a 4, which is going to expand it even more and make it increase, your Y value increase so much faster. So if your A value is going to be a 2, a 3, a 4, something like that, your graph is going to get skinnier, because it's going to rise up, that Y value is going to increase at a much faster rate. On the flip side, if that A value is between 0 and 1, or technically negative 1 and 1, we'll say negative 1 is less than A, which is less than 1. So if A is between negative 1 and 1, your graph is going to get fatter or widen out, because we're going to take that number here that's cubed and take a fraction of it, which means going to make it a smaller portion. And so then you're going to have a graph that's going to go maybe more like this. And it widens it out. So what's the conclusion we can draw from this? Whenever we are in a generic form of y is equal to a times the quantity of x minus h to some power, in this case cubed, plus k, the k is always a vertical shift for us. It tells us whether we're going up and down, and we keep the same sign. So if it's a plus 3, we go up 3. If it's a minus 3, we go down 3. The horizontal shift is the h for horizontal, and it's closest to the x, so it's going to be on the x-axis, or the left-right axis, the horizontal. And it's the opposite sign of what we think, because the generic form says x minus that quantity. So if it looks like it's x minus 2, it's actually going right 2. X plus 2 is actually going left 2. And A tells us two different things. It tells us whether our graph is rising up or if it's flipped over the opposite direction from positive or negative. And then whether it's a number between 0 and 1, it's going to be wider. If it's greater than 1, it's going to be a skinnier graph. Now this is going to hold true for all of our equations. It happens the same thing for a parabola. It happens the same thing on a radical form. It happens the same for our v's of absolute values. All of these have the same shift, the same types of shifts, the transformations, depending on your generic form. So you identify what kind of graph it is by the highest exponent. In this case it was a 3. So you know that it's going to be a cubic and what that looks like. And then you can do your shifts from there. That's the easy way of doing transformations.